Hey everybody, Dr. Retzek here with you. This is our second video in section 7a, where we're talking about the adjoint of a linear map from V to W. Let's get started. So the story is we have this picture. T maps left to right from V to W, and it's got this cousin T star that maps right to left, where the connection between T and T star is that they're complementary in a very specific way. If you take the inner product of TV with W, that's the same as taking the inner product of V with T star W. Now, you have some things to keep track of, even in that seemingly simple statement. The inner products are not the same. One of them is happening on the right-hand side of the picture, and the other is happening on the left-hand side of the picture. So TV and W, those both belong to big W, and therefore, that inner product is happening on the right. On the other hand, little v and T star W, those are both in big V. So that inner product is happening on the left. But they match, and that's how T and T star are relative to one another. Today's discussion is all about properties of the adjoint. So we're going to list a bunch of things. We'll talk about how to prove them, maybe prove one or two. These are just tools of the trade that you just want to have ready to go anytime you're working with adjoints. Okay, so here are some properties. I think these are maybe theorem 7.6 in section 7a. All right, here are some properties. Let's say you had two different mappings from V to W, S and T. Well, then you're free to add the two mappings. And you might wonder, well, what is the adjoint of S plus T? And the beauty of it is, it's just the adjoint of S plus the adjoint of T. Or maybe you're going to scale a mapping T by some factor, lambda. Well, the beauty of that is, the lambda just pops out in front, only you pay with a lambda bar. So the adjoint of the mapping lambda t is lambda bar times the adjoint of t. Let's see here, what else? What else we got? Oh, here's a good one. If you take the adjoint of the adjoint, well, you're back where you started. So T star star is just T. In the special case that you're talking about the identity operator on a vector space V, so identity from V to V, if you look at the adjoint of the identity, it's just itself. Unsurprising. And finally, another way that we sometimes combine operators or mappings is we compose them. If you were interested in the adjoint of the mapping ST, oh, it's so tempting, but it's not quite right. Think about this for a sec. If you do T and then do S, if you're trying to work your way all the way back right to left, it should be undo S, then undo T. So the adjoint of ST is T star S star. Now let's talk about how one proves something like this. Let's say you were interested in proving part B. If you want to prove part B, Think about the equal sign in part B. What kind of an equal sign is that? It's not set equality, it's equality of mappings. So you're trying to show that lambda t star does the same thing to W as lambda bar t star does. So let's just see what happens. So let's think about V and then adjoint of lambda t acting on W. All right, let's think about what that is. Well, by definition of adjoint, that's lambda t acting on V, inner product with W, which is lambda TV, inner product with W, which is TV lambda bar W, that's conjugate homogeneity in the second slot, which is V, inner product T star of lambda bar W. But T star is linear, so that's V lambda bar T star on W. And so you can see these two quantities match. And since it's V in the first slot, in the first expression and the last expression, the underlined purple quantities agree. And that's true for any W. And that's how most of these proofs go. You should follow up on A through E, not including B, just to make sure that you got this move where you're flipping the T and the T star back and forth in the first and the second slot to purchase the information that you want. But that's how all those proofs go. Okay, so there's some properties. Let's see them one more time before we leave. Take the adjoint of the sum, it's the sum of the adjoints. Scalar multiplication, the scalar pops out as a conjugate. If you do the adjoint twice in a row, you have the map you started with, adjoint of the identities itself. And for products of linear maps, which remember represent function composition, the adjoint of ST is T star S star. Okay, now there's another few properties that are also noteworthy and good to just have with us when we need them. So these next ones are having to do with the null space and the range of T and T star and how they're related to each other. I mean, T and T star are cousins. And so subspaces that are sort of intrinsically connected to T or T star must have something to do with the other one. This, I think, is pretty much theorem 7.7 in 7a. Okay, so if you're talking about a linear map from V to W, let's think about the null space of the adjoint. So say you have little w that belongs to the null space of the adjoint. Okay, so little w is on the right side of this picture, and T star sends it right to left to 0. Fantastic. So the inner product of V with T star W which is TV inner product with W, is 0 because remember, this T star W is 0. That's what it means for W to be in the null space of T star. So T star W is 0. So if you inner product with T star W, you get 0. But inner producting with T star W is the same as TV inner product with W. And that's true for any V whatsoever. Okay, read this. That says W is orthogonal to any TV. So, in other words, W is in the perp of the range of T. Okay, now look at this little argument. We started with a W in the null space of T star and concluded that it was in range T perp. So we just proved that null T star is a subset of range of T perp. But our proof can be read forwards and backwards. These are all equivalences. And so we have shown null T star equals range T perp. And that's kind of the master key there in 7.7 in your book. You establish this one with a math 248 kind of subset both ways sort of argument. And then once you have the red box, a bunch of other stuff follows. So you get a bunch of and. And what if you perped both sides? Then null T star perp is range T perp, which is range T. All of this is happening in finite dimensional vector spaces here in chapter 7. But you could in the red box, instead of perping both sides, what if you just switch the roles of T and T star? Then you would also have this. Look at that red box and change all the T stars to T's and all the T's to T stars. Then you get null T is range T star perp. And then if you believe that one, you could perp both sides of that if you felt like it. So 7.7, in the book, it looks like it's 4 statements. It's really 1 statement. It's the red box. Anyway, we could perp both sides of that if we felt like it. And that tells you how the null space and range of T and T star are related to each other. Anyway, that's 7.7. Finally, in this hits list of connections between T and T star, let's think about matrix representations. Okay, so remember our picture. This is what's going on right now. You got V, T maps V to W, T star goes the other way. Okay, now, for the purposes of matrix representation discussion, let's assume V is endowed with an orthonormal basis E1 through En. So those are On. And then W is endowed with its own orthonormal basis, F1 through Fm. No claims here that n and m are the same. V and W don't have to have the same dimension. Okay. Now let's think about how you would make the matrix representation for T. So it would look something like this. It would be a big old matrix. The matrix would have m rows and n columns. Now let's think about, say, the kth column of that matrix. That's the kth column among many. Okay. Remember how you get the kth column in these matrix representations. You take EK from the left, you send it over, it lands over in W, then because F1 through Fm are a basis for W, you can write TEK in terms of the Fs, and the coefficients in that expression are what you plop down in that kth column. So I'm going to say it like this. Can write TEK in terms of the Fs, but the Fs are orthonormal. So you actually know exactly what linear combination of those Fs produces the vector TEK. And that combination is TEK with F1 times F1 plus ... TEK with Fm times Fm. That is the linear combination of the Fs that produces TEK. And these coefficients here are exactly the entries of that kth column. Now let's say you wanted the jth entry of that kth column. Say you wanted to see what was in the jth row of that kth column. Well, you would come down here and you would find the jth coefficient. And the jth coefficient is TEK, inner product with Fj in particular. Okay, so take one more look with your eyes at that representation for the matrix for T. We know what's in the jth row, kth column. Okay, now T star runs right to left. So we're going to use that same reasoning to simply assert jth row, kth column of the matrix for T star is, okay, now keep track. You have to change the T's to T stars and switch the roles of the E's and the F's, because now if it's T star, the F's are the basis in the domain and the E's are the basis over in the range. Okay, so jth row, kth column of the matrix for T star is going to be T star Fk inner product Ej. But this is delightful because you know how T star and T are related. This is actually Fk T Ej, which is Tej Fk. It's a pretty bad angled bracket. All conjugate, because any inner product has conjugate symmetry. Now look what that is. That is conjugate of kth row, jth column, kth row, jth column of M of T. Now read all that. This is fantastic. If you want the jth row, kth column of the matrix for T star, that's nothing other than the kth row, jth column, conjugated of M of T. In other words, if you want to see it in the matrices, this is what you're seeing. We just proved this. If you want the matrix for T star, and it looks something like that, and you have the matrix for T, and it looks something like this, let's say you're in the third row, 7th column for T. So this is third row, 7th column. We just proved that in the 7th row, third column of T star, you have the conjugate of whatever was in the third row, 7th column of T, which makes these matrices conjugate transposes of one another. So you just flip rows and columns and conjugate everything. And that's how you get from the matrix for T to the matrix for T star. So this discussion was just about all the connections between T and T star. You've got matrix representation connections. They're connected by conjugate transpose. You've got null space and range connections. And you've got a bunch of properties of how starring linear maps works. Okay, this idea of the adjoint is going to purchase deep, deep linear algebra results for us. Okay, that's it. Read along in the book and let me know if you have any questions, and I'll see you in class. Bye.